Assalamualaikum and hi to Dr. Abdul Malek. Today our group we're going to present about application of geometric linear programming in the manufacturing sector. We are from group 10. First of all, I want to introduce our group members. First is Lim Boon Qi, metric number 277532. Next is me, is Muhammad Faiz bin Abdul Halim, metric number 264181, and last is Fang Soo Ying, metric number 270547. First is introduction. Many real-world challenges entail maximizing or minimizing a given quantity while adhering to certain constraints. This type of problem can be approached in several ways, one of which being geometric linear programming. We will explore examples of maximization of a linear expression in any numbers of variables while adhering to some linear constraints. This method is used to solve a wide range of problems in the manufacturing industries.
Good day, Doctor. My name is Fang Soo Ying and my matrix number is 270547. Now I'm going to explain what is geometric linear programming. Geometric linear programming is where there is a given linear expression z equal to ax plus by in two variables x and y, and we need to find the values of x and y that maximize or minimize z and subject to the linear constraints. The function z is called an objective function. In the below condition, any one of the symbols can be used. The first constraint is like a1x plus b1y, and the second constraint can be written as a2x plus b2y and follow. And also we must remember that the x and y must be equal or greater than 0. Next is the feasible solution. A feasible solution is one that satisfies all constraints x and y. The feasible region is a subset of the xy plane that contains all possible solutions. The feasible region is then an intersection of finitely many lines and half planes. The feasible region is bounded if it can be encompassed in a sufficiently large circle, otherwise it is called unbounded. The diagram on the left-hand side shows bounded feasible region, and the lower side show the unbounded feasible region. Bounded feasible region. Objective function will attain both a maximum and minimum value, and this occur at extreme points of the feasible region.
So for me, my name is Lim Boon Qi and metric number is 277532. I'm going to present about for the example analysis of the problem and the solution. So for the example is about a candy manufacturer has 170 puffs of chocolate covered mints and 130 puffs of chocolate covered berries in stock. He decided to sell them into alternative mixtures. One mixture will contain 2/3 mint and 1/3 berry by weight and will cost for $1.25 per pound. The other mixtures will contain half mint and half berry by weight and will cost for $2 per pound. To maximize his sales revenue, how many puffs of each mixture should the candy manufacturer prepare for? So for the next one, I will explain for the analysis of the problem. For the first, I will let A for the mixtures of 2/3 mint and 1/3 berry, and let B for the mixtures of half mint and half berry. And at the same time, I will let S be the number of pounds of A to be prepared, and let Y be the number of pounds of B to be prepared. Since mixtures with A will cost for $1.25 per pound and mixtures B will cost for $2 per pound, thus the objective function, or also known as revenue function, can be written as z equal to 1.25x plus 2y. Since each pound of A consists of 2/3 of mint and each pound of B consists of half mint, the total number of pounds of mint used in both mixtures is 2/3x plus 1/2y. Also, the question has mentioned that the candy manufacturer can use at most 170 puffs of mint, so we have the constraint 2/3x plus 1/2y less than or equal to 170. Similarly, since each pound of A consists of 1/3 of berry and each pound of B consists of half berry, the total number of pounds of berry used in both mixtures is 1/3x plus 1/2y. Also, the question has mentioned that the candy manufacturer can use as most 130 pounds of berry. So we have the constraint 1/3x plus 1/2y less than or equal to 130. Also, we must have x greater than or equal to 0 and y greater than or equal to 0. The above problem can be formulated as follows. Find x and y that maximize z equal to 1.25x plus 2y and subject to the constraint below. Next is solution. So for the first one, we will find the corner. We will let x equal to 0 in this equation and we will get y equal to 340. So for the order pair is 0, 340. And at the same time, we also will let y equal to 0 in the same equation and then we will get x equal to 255. So we will get the order pair 255, 0. Similarly, we also will let x equal to 0 in this equation and we will get y equal to 260 and we will get the order pair 0, 260. And also we will let y equal to 0 in the same equation and we will get x equal to 390. So for the order pair is 390, 0. Second, we will graph the point and shade the feasible region. From the first step, we have find out these 4 points already so that we are able to draw these 2 lines. And this feasible region is stated by following these all conditions. And for this point of intersection, we will explain in the next step. For the third one, we will find the point of intersection of the 2 lines. So we will let 2/3x plus 1/2y equal to 170 as equation 1 and let 1/3x plus 1/2y equal to 130 as equation 2. Equation 1 minus equation 2 will get x equal to 120. To get the y value, we will substitute x equal to 120 into equation 1 and then we will get y equal to 180 so that we are able to know that point of intersection is 120, 180. For the last step, we will substitute the value in the objective function. We already know all the extreme points to the graph, which is 0, 0, 255, 0, 120, 180, and for the last one is 0, 260. So to find the value of z, we will substitute all the x value and y value into the z function, and we will get the value of z. For the point 0, 0, we will get the value of z equal to 0. For the point 255, 0, we will get 318.75. For the point 120, 180, we will get 510. For the point 0, 260, we will get 520. Since the table shows that the largest value for z is 520 and the corresponding optimal solution is 0, 260, thus the candy manufacturer attained maximum sales of $520 when he produced 260 pounds of mixture B and none of mixture A. So that's all from me.
So in conclusion, geometric linear programming is a powerful tool for deciding between options in a decision problem, and it has been used in a wide range of problems. Any of the geometric linear program consists of 4 parts: a set of decision variables, the objective function, the parameters, and a set of constraints. Except the above example shows that application of geometric linear programming in manufacturing sector. It also used to solve various problems in finance, economics, and life science that often require us to make decisions based on a set of conditions. That's all from our group. Thank you.